So if we go and we look at what our complex could be, we're going to have a cobalt, and that cobalt is going to be directly bound to NH3. And there's going to be 6 of them there. If we think about what we studied in the Vesper shapes, what type of shape do we have if there's 6 surrounding atoms or 6 ligands associated to it? We have an octahedral. And octahedral geometry is a very, very, very common geometry in chemistry. So we have this octahedral complex, and then those other extra Cl's are going to be our counter ion. So this portion is our complex ion, and we denote that in brackets. And then we also have a counter ion. There are various ways we can experimentally determine this. We can use the silver chloride. We can carefully measure this out. We can look at the conductivity of the solutions. And this is exactly what you guys are going to do in lab next week, is you're going to look at conductivity measurements, and you're going to make some calculations based on the experiments that Werner performed way back in the day. Okay? So this is how we commonly now denote these particular complexes. Notice that if we have 3 chlorides on the outside of these brackets, that means our complex ion has to have a +3 charge. And the charge of the complex ion is going to be dictated by how many counter ions that we have on that particular complex. So if we wanted to write this, we can say that the CO3+ is bound directly to 6NH3. This tells us that this complex ion has an octahedral geometry. So if we wanted to draw this and draw them in 3 dimensions, we have the cobalt at the center, and we're going to surround this with 6 NH3s. Learn to think and be able to draw these shapes in 3 dimensions. Because when we go and we start talking about some more of the advanced concepts here, you're going to have to be able to visualize these things in 3 dimensions. So if we have this cobalt complex, we draw all 6 of these NH3s directly bound to it. Now, one of the things I'm going to note that when I'm drawing these, here I drew the first 4, and they look perfectly fine from what you would think. Whenever I draw these next 2 NH3s, typically chemists draw structures to show the atom on the ligand that is directly bound to that transition metal. So if I put this nitrogen here, I'll write this NH3 kind of backwards compared to what you would normally see that. The reason we do this is because if you think of that ammonia shape, the ammonia has a lone pair of electrons on it. That lone pair of electrons is sticking out, and it's going to be attracted to the cobalt 3+. That's where the bond happens, or what we call a coordinate covalent bond, that happens between the cobalt and the ammonia, and that's directly through the nitrogen. So we kind of sometimes draw these a little weird to emphasize that it's the nitrogen that's bonding directly to the transition metal and not the hydrogens. When we draw this complex ion right here, we usually put brackets around it and then indicate its charge. In this case, it's 3+. We can do the exact same thing for the COCl3.5 NH3. In this case, we're going to experimentally determine that there are 2 Cl- ions in solution. So what this tells us is that when we look at the shape or the geometry here, if there are 2 Cl minus ions in solution, and we have a total of 8 various ligands that could bond to the transition metal, that means that this cobalt right here is going to have 5 NH3s plus 1 Cl minus directly bound to it. So when we draw our complex ion, it's going to be a cobalt with 5 different ammonias and 1 Cl. And this isn't going to be a 3+ complex ion anymore. It's going to have a 2+ charge because there are 2 Cl minus ions that are the counter ion. In terms of the colors of these particular complexes, this one up here is orange, and this one down here is like a purple color. If we do the same thing for the COCl3 with 4 equivalents of ammonia, we have a green-violet potential to get either color. So there's got to be something more in terms of what's happening and what we can do to account for those colors. So when you put a different amount of ligands around a particular complex, you can have different scenarios that happen. So if we look into the COCl3.4NH3, again, hopefully you start seeing a trend emerging here. And experimentally, if we were going to try to dictate what's happening here in the solution, the cobalt 3+ is bound to 4 NH3 and 2 Cl minus. And we can determine that there is 1 Cl minus ion in excess in solution. So our complex ion is going to look, or the structure that we're going to write for the complex ion is going to be CO NH34 Cl2 with 1 Cl as our counter ion. That means our complex ion has to have a +1 charge.